Here we'll talk about work and kinetic energy and how they're related for a single particle. Let's consider a system that consists of one single particle, and from the outside, from the environment, we have an external force that is being applied to this particle. So we have a constant force that is parallel to the direction of motion, and it's pushing on the particle as that particle undergoes a displacement, delta S. Here we use delta S just because we're saying that this is a displacement in any arbitrary direction. It doesn't have to be the x direction or y direction or any specific direction. But in this case, the particle is the object in motion. That's the system that we're looking at. And so the force that's acting on it from the outside, that force is coming from the environment. So this is not a closed system. Energy is not conserved here. But we are looking at this external force, what work that's doing to the system, and how that will change the energy of the system. So when we look at before this force begins to be applied, our object has a velocity, and we said that the force is being applied parallel to that velocity. And so we know that if the force is being applied parallel, there's going to be an acceleration in the same direction. And if there's an acceleration, that means in the same direction as our velocity, that means that our velocity will get bigger after that force has taken place. Since the velocity is getting bigger, that means that our kinetic energy has increased. So we would say that the kinetic energy has increased, which means that the kinetic energy at the end is greater than the kinetic energy at the beginning, which makes sense because we're going faster at the end than we were at the beginning. And this change in kinetic energy is equal to the work done by the outside, by the external force. And that work done by an external force is positive because you have the force being applied in the same direction as the displacement of the particle, as the net motion of the particle. We define here what we mean by kinetic energy. Kinetic energy is defined as 1/2 mv squared, where m is the mass of the object and v is the velocity of the object. Here, because it's v squared, we're really looking at the speed or the magnitude of the velocity. And so if you're looking at an object that's in motion, by virtue of being in motion, this object has kinetic energy. This kinetic energy is a measure of the effort that was needed to accelerate that object, to get it going from 0 to whatever speed it happens to have. The amount of the kinetic energy depends on the particle's mass. The heavier the object, the more effort will need to go into accelerating it, because force is mass times acceleration, so a greater mass will require a greater force applied. And the speed of the object comes into play as well, because we're looking at how fast the object is going. The faster it's going, the more acceleration it will take to get it up to that speed. But we don't care about the position for kinetic energy. We just care that the object is moving in whatever direction or from whatever position it may be. When we look at a single constant force on a single particle, the kinetic energy changes in proportion to the distance traveled. What that is saying is that the change in kinetic energy is proportional to the force times distance, which is the work done by a constant external force. And when we talk about kinetic energy, it has SI units of joules, where a joule is a kilogram meter squared per second squared. It's also written as a capital J. As we mentioned, work done on a one particle system is energy being transferred to the system by an external force. This energy is manifested in a change, in an increase in the kinetic energy of that particle. So we see in this equation here that the change in kinetic energy is equal to the work done by an external force. So if external work is being done, if positive external work is being done, that means there's a positive acceleration, which means the particle goes faster and its kinetic energy is greater. If there's negative external work being done, that means there's a negative force, a negative acceleration, which is decelerating the object, taking away its kinetic energy and slowing it down. If we have the case of a constant force that is parallel to the direction of motion, again, this s-axis, this arbitrary direction, then we can treat work as an integral. We're looking at how much force is being applied over a short distance. The integral is adding up all those little distances to find the total amount of work done over a total distance. If the force itself is constant, it can be pulled out of the integral. Integrating ds just gets us the change in position or the displacement along that line of axis. When we talk about work, the SI unit for work is still the joule. Work and energy are measured in the same units. There are different ways of thinking about the same thing. Energy is something inherent to an object. It is something that an object has. Work is the transfer of energy to or from that object or system. And it's a measure of how much energy is being transferred to or from that system. And so it's measured in the same units. When we talk about work, work can be either positive or negative. If the force causes the particle to speed up, that work is positive. For the force to cause the particle to speed up, that means that the force has to be parallel with the displacement, either both of them in the positive direction or both of them in the negative direction. In either case, we know that if the acceleration and the displacement are aligned, the velocity will increase. And if the magnitude of the velocity increases, that means that the kinetic energy is increasing as well. However, we can also have negative work. That's when the object slows down and loses energy. Negative work is when the force is anti-parallel, it's in the opposite direction as the displacement. In that case, as the object moves in one way, the force is acting in the other way. The force is causing a deceleration, which is taking away kinetic energy, and that deceleration slows the object down, makes the magnitude of its velocity less. And so when we want to look for the sign of work, we look at the direction of the force and the direction of the displacement. If they're both in the same direction, that's positive work. If they're in opposite directions, that's negative work. If you have no displacement, you have zero work, because you can apply a force that doesn't do any work. For example, if you have a book sitting on a table, there's a force of gravity and a normal force, but the system isn't in motion and nothing is happening, so there's no work being done, there's no energy being transferred. It's also common to have a constant force and a constant direction that is not aligned with the displacement. For example, in this system, our object is moving along this inclined plane. There's a direction of displacement. The force is constant, but it's constantly at an angle with the displacement. In that situation, in order to find the work being done, only the component of the force that is parallel to the displacement, only that value of the force counts towards the work. The other component of the force, the perpendicular component of the force, is still there, but it is not doing work on the object, and it's not causing the object to speed up or slow down. The way that we can find this is by, instead of using the total value of the force, we want to use the component of the force that's in the s direction. Looking at our graph here, we see that that component would be found using a cosine theta. So basically here we have the component of F that's projected in the s direction along our line of motion. Since the force and the angle are both constant, we can pull those out again, and we see that the work done for a given force and a given displacement, when the force and the displacement are not aligned, when they're not perfectly parallel, we can find the total value of force by including a cosine theta, where here theta is the angle between the force and the displacement. So basically here this value of theta is projecting the force into the direction of the displacement, so that we're looking at the component of the force that's acting along the line of motion that is contributing to the work being done. When we look at force and displacement, force can have any angle relative to the displacement. In the first situation, the force is already perfectly parallel with the displacement. In that case, the work done is the magnitude of the force times the magnitude of displacement, because there's a 0-degree angle between the two. They're both perfectly parallel. They're both pointing to the left, to the right in this situation, and because they're pointing in the same direction, that work is positive. If there's an angle between the force and the displacement, an angle that's between 0 and 90 degrees, in that case, we only want to use the component of the force that is parallel to our direction of motion, and we don't want to use the component of the force that's perpendicular, which doesn't count towards our force. In order to find that projection of the force, we have to include a cosine theta, which gives us the parallel component of the force times the displacement along which our particle moves. In this case, though, even though the force and the displacement are not perfectly aligned, they're still in the same direction. They're both tending to the right here, and so the sign of the work will still be positive, because the force still has a component in the direction of the displacement, and so that's still a tangential acceleration that we'll see. It's possible also for the force to be perfectly perpendicular to the displacement. For example, if we're pushing a book across a tabletop, the force of gravity will always be perpendicular to the motion. The normal force will always be perpendicular to the motion. And so if we apply a force and we move this object across the tabletop, the normal force and the gravitational force will always be perpendicular to the motion, and so both those forces will do 0 work as we move across the tabletop. That's because when we look at the projection of the force into the direction of the displacement, they're perfectly perpendicular, so there is no component in this case. When we try to multiply by the cosine theta term, we have cosine of 90 degrees, which is 0, which tells us there's no work being done in that case. Finally, we can have a force that's being applied that is anti-parallel to the displacement. In this case, the angle theta is greater than 90 degrees. We're past a perpendicular, past a right angle, up to 180 degrees. In this situation, the work done is still F times R times cosine theta, but if cosine theta, if theta is between 90 and 180, then cosine theta is less than 0, is a negative number for theta between 90 degrees and 180 degrees. And so if you use this angle, it will automatically give you a value of the cosine, a value of the work that is negative because of that cosine term, because the fact that the cosine is less than 0 is negative in these values of theta. The reason why we're getting that result is that when we project the force into the direction of the displacement, we see now that the component of the force that's in the direction of the displacement is actually anti-parallel. It's actually in the opposite direction. So here we have a velocity to the right, but our force is to the left. Our acceleration is to the left, which means that our velocity will be getting smaller, and so our kinetic energy is getting smaller because this force is taking energy away from our particle. This is maximized when theta equals 180 degrees, when cosine is equal to a -1, and that's where the negative sign there is from the cosine term. The work is negative, and in this case, the force is perfectly anti-parallel with the displacement, and so the force, the full value of the force, is taking energy away from our object as that object moves. We've seen that the work done is force times distance, or force times displacement, over a short direction. And this assumes that the force and the displacement are aligned. We can use a cosine theta if necessary to project them into the same direction. Thus far, we've assumed a constant force, but that doesn't have to be the case. We can also have variable forces, and if that's the case, our equation becomes the integral of the force integrated ds. So what we're looking at is, for each little tiny piece of motion, how much force is being applied or is opposing our object as it covers each tiny motion. If we integrate from the starting point to the ending point, we get the total amount of force over the total distance that's being applied. In such a situation, you'd have to be given the force to be able to find that otherwise. But if you want to find the work done, you can either evaluate the integral geometrically. If you're given the force as a function of distance, you can find the area under the curve, which is equivalent to taking the integral. Or you can actually do the integration directly, analytically, where perhaps you have the force as a function of position, and you can integrate that directly. There are a few special situations, a few special cases of work. One of them is for uniform circular motion. In that case, if you're following uniform circular motion, we've said that your displacement and your velocity are tangential to your circular path at every point along the circular path. However, if you're following a circular path, you must have a centripetal force that always acts radially inward, pointing towards the center of the circle. Since the component of the force since the force is always perpendicular to the displacement, there's zero component that is parallel to the displacement, and thus there's never any work being done as you go around a circular path with uniform circular motion. This is how satellites can stay in orbit. This is how the moon can stay in orbit around the Earth, because as they follow nearly circular paths, they're always being pulled inward by Earth's gravity, but there's no work being done, and so there's never a loss of kinetic energy that would cause a satellite, would cause the moon to crash into the Earth, because there's never any work being done. So to sum that up, if a force is always perpendicular to motion, it does no work. And if it does no work, then the change in kinetic energy has to be zero, meaning the kinetic energy has to stay constant as you go around such a circular path. For another special case, consider a roller skater who straightens her arms and pushes off of a wall, as shown in the figure here. The skater has a force that she's applying to the wall, and by Newton's third law, the wall is applying a force on the skater as well. As she pushes off, her center of mass is displaced. She's moved away from the wall, but the palms of her hands, which is where the force is being applied, her hands are not moving as she pushes away from the wall. Thus, the wall is applying a force, but it doesn't cause a displacement because the force is pushing on her hands and her hands are not moving. Thus, the wall is doing no work in this situation. If you look a little bit deeper, you would find that her wrists or elbows are pushing against her hands, and she is causing a displacement against herself, a displacement against the wall, and you would find that she is doing work on herself, that if she did this over and over again, she would end up with tired arms, which shows that she's giving up energy, she's using up her own energy to move herself in this situation.